In continuation with our series of lectures on inner product spaces, we have come to the last lap of it, namely proving the spectral theorem wherever it is possible. In fact, we show that for all normal operators in an inner product space, we are working on finite dimensional inner product spaces over C, the diagonalization is possible. That means the spectral theorem is valid. We shall explore this in detail. We have already done the essential groundwork for working on this. Namely, we have proved a few results on this. We had been primarily concerned with three types of operators. All of them are normal operators, but normal operators with certain specialities, like the self-adjoint operator, the unitary operator, or what you call isometry, and the general normal operators. Now let me start with the basic notations, etc. We have X an n-dimensional inner product space over C, and T is a linear transformation over X, and we assume that T is normal, namely T commutes with T star, that is T star is equal to T star T. Under these assumptions, we show that T is diagonalizable. That means there exists a basis for X with respect to which the operator T has a diagonal representation. Now this is the ones for which T equal to T star, and therefore T star equal to T star T. So it's normal. Then you have got unitary operators or isometric operators. So every self-adjoint operator is a normal operator, every isometric operator is a normal operator, and you have the general normal operator which may not be self-adjoint or isometric. Now in all these cases the diagonalization is possible with the specialities. Now the specialities concern the spectrum of these operators. Okay. For self-adjoint operators, so let us start with, for self-adjoint operators, all eigenvalues are real. For isometric operators, all eigenvalues are lie on the unit circle Now, for general normal operators, you cannot say that. Okay, right. So, these two features are there. Apart from that, the eigenvectors distinct eigenvalues of T are orthogonal for any normal operators. Normal so it is equally well valid for self-adjoint operators and isometric operators. So these are some of the features that you have. Now we have some more information about these operators. Now if T is self-adjoint, or isometric, and M is an invariant subspace of T, then M perp is also this happens in both these special cases, namely self-adjoint operators as well as isometric operators. Okay. See, another important feature of a normal operator is that if X is an eigenvector T, assume normal, then belonging to the eigenvalue for lambda, then X is also an eigenvector of T star belonging to eigenvalue lambda conjugate, which simply tells that if lambda is an eigenvalue of T, then lambda conjugate is also an eigenvalue of T, and then both T and T star have X as an eigenvector. In the case of T, it belongs to lambda. In the case of T star, it belongs to lambda conjugate. Now this is the interesting relationship. Okay. Now in the special scenario of So in the case of a normal operator, if M is an is the eigenspace of T belonging to the eigenvalue then M is invariant under T. Further, M perp is also now what you have is that in this scenario, if any subspace is invariant under T, M perp is also invariant under T. Here we are specifying this the particular subspace M to be the eigenspace. Okay, and in particular this statement is valid for all self-adjoint and isometric operators. So this is the crucial result that we will be using in our theorem. What is the consequence of this result? Consequence of this result is that now we know that X is equal to, since both is the eigenspace of eigenvalue lambda. Then what we have said is that both M and M perp are invariant under T. T reduces on M and M perp. So if we call this, let now what you can immediately show is that obviously Tm and what you can say is that both T and Tm perp are normal operators. So this much of results we can exploit to show that T is diagonalizable. So we now write the main theorem. T diagonalizable. Now this is the main theorem that you want to prove, and the consequence is that the spectral theorem is valid. That we shall show towards the end. Okay. So we observe that since the field that we are using is C, which is algebraically closed, now the characteristic polynomial of T of degree n splits into products of linear factors. Okay, so that is one information that we are going to use. So recall that the characteristic polynomial this is the dimension of the space, splits into product of so it is of the form. So if you call this characteristic polynomial as f lambda, so that is if the characteristic polynomial P P then P lambda RK, where R1 plus of course you have 1 less than or equal to Ri, each Ri is this is equal to n. All are positive integers and they add up to n. Thus, the algebraic multiplicity of lambda I is Ri. The algebraic multiplicity of now recall that the algebraic multiplicity, the operator T is diagonalizable if the algebraic multiplicity of each of these eigenvalues is equal to the geometric multiplicity. The geometric multiplicity is of lambda I is the dimension of the eigenspace of T belonging to the eigenvalue lambda I. Lambda I, namely the dimension of the eigenspace belonging to is denoted by Mi. Then T is diagonalizable if and only if Ri is equal to that means the algebraic multiplicity of each eigenvalue is equal to the geometric multiplicity. That is, the algebraic multiplicity of each eigenvalue is equal to its geometric multiplicity. Therefore, our strategy to prove this theorem, that whenever T is normal, the algebraic multiplicity of each eigenvalue is equal to the geometric multiplicity. Okay, so let us start our work. Okay. So we try to show this result. So let us start with, let mu denote eigenvalue of t. Let R be the algebraic multiplicity of mu, and then we prove, then we show that R is equal to that's a strategy. Okay, so we start with M. So let the set of all x belonging to x such that t minus that is the eigenspace of t belonging to the eigenvalue Now what we do is we use the normality property of T in the form that T leaves M invariant and T also leaves M per invariant. Then clearly what you have is that x is equal to m plus m bar. M per, and further dimension of these are all the consequences of that, and T restricted to T leaves both M this is the crucial result that we use, which is an offshoot of T being normal in our proof. Okay, now look at Tm. Tm and are normal operators on respective. Assume, okay, we have already assumed this. Now our claim is that M is equal to R. Our claim is that M is equal to R. Now we observe that the characteristic polynomial of Tm because the dimension of the space is M and it's an eigenspace belonging to the eigenvalue mu, therefore this is the characteristic polynomial of this. Now you see that P lambda can be written as lambda minus mu to the power M into some Q lambda, where Q lambda is the characteristic polynomial of and what you have is that T is equal to T plus Tm plus Tm perp. That's fair. So this is quite easy to show. This follows from the invariance of M perp under T. Now our strategy for proof is this. Assume R is different from M. So in fact R is greater than M. So we show that it leads to a contradiction. Strictly greater than R not equal to M. Then what happens is lambda minus mu is a factor of Q lambda, the characteristic polynomial of Okay, therefore there exists such that t minus mu I zero, that is t minus mu I equal to 0. Because y not equal to 0. What does it mean? This implies y is an eigenvector of t. Y is an eigenvector of t belonging to mu. Eigenvalue mu of t, but y does not belong to M, contradicting the assumption that that is the eigenspace of that means M consists of all the eigenvectors of mu of t belonging to the eigenvalue mu. Okay, so this is the contradiction that you get, right? Because y does not belong to M, so it contradicts this. Therefore, we have R. Now the mu that you have chosen is arbitrary, since the choice of mu it follows that for any eigenvalue of, for every eigenvalue its geometric multiplicity, its algebraic multiplicity, equals what does it mean? That means T is factorized. Now this implies T is diagonalized. This is the main theorem. So that completes the proof of the theorem. Okay. So every normal operator is a diagonalizable operator. Now let us write down the spectral theorem. So we are in now a position to write down the spectral theorem. At eigenvalues of T with respective eigenspaces. Then what we have is that Mi is orthogonal to Mj not equal to K. That means eigenvectors belonging to distinct eigenvalues are orthogonal. So that is a consequence of that. Another consequence is that the dimension of n. Further you have x is equal to this is equal to n. Okay, and they are independent also. These spaces are all independent. Therefore, any x belonging to x is equal to xk, where this is a unique breakup of as sum of So what we can do is define Pi xi. Pi square equal to Pi, and each Pi is a projection on along my prime, where further xi therefore these are orthogonal. Associated with so what do we have? We have the following. So x equal to x1, which is equal to that is x is equal to what does this mean? This implies This implies I it is one result. Further, Tx equal to Tx1 this is equal to lambda 1 this is true for every x belonging to x. Pk. Now these two statements together and the existence of these pi's gives the spectral theorem. Okay, so now we can state the theorem. If T is normal, so we will write down the statement of the theorem. Is normal distinct eigenvalues. Each further okay, and if pi is from X to Mi. Unique orthogonal projection on Mi. Further, I equal to Pk further the resolution of identity associated with T, and T is equal to now this is the spectral theorem. That means given T there is a unique resolution of the identity given by I written as the sum of a set of orthogonal projection operators, and T can be written as a linear combination of these projection operators. Now this is the beautiful consequence of the diagonalizability of a normal operator. Now what we want to do is, how does the matrix representation looks like? Okay, so let us do that, and then that will finish everything. let bi ordered basis for M1. Then B is an ordered basis for X. Then the representation matrix ordered basis B is then given by where is 0 here. This is the diagonal form that emerges. So each block having so you get a there are k blocks in this representation and each block is diagonal. With the diagonal entries of the ith block. So you have got the first block. This is a M1 cross M1. This is M2 cross M2. This is Mk cross. This is an n by n matrix. That's the setup that you have. This is the spectral theorem. Okay. So that completes the proof. Okay, thank you very much. Let me conclude the talks at this stage. Now I just want to make a couple of remarks. One, of course, this is equally well valid for self-adjoint operators. Now the special advantage that you have is that all the eigenvalues, that is all the lambda i's, are real. For the isometry, which is also a normal operator, with the T star as the inverse of T, you have all these eigenvalues lambda i's are located on the unit circle in the complex plane. That means modulus of lambda I equal to 1 for every I. That's a special case of it. And of course, in the real case, what happens is that we have proved the theorem that in the real case all the eigenvalues are real. Okay. Now, how do you know that you have accounted for all the distinct eigenvalues? Now, that comes from an application of complexification of the real operator. Okay. Therefore, the complexified form also has the same eigenvalues as that of a real operator. I mean, that's a special case when you are working on the real operators. Since all the eigenvalues are real, now you see that the operator, when it is a real operator, that means when we use the associated field as R, you can catch all the eigenvalues on the real line, and you see that you have a breakup of this. The same theorem is valid, but now all the eigenvalues will be real. Okay, thank you very much.